Okay, good morning, everybody. Welcome to the 2021 Heterocycles. So this year we're going to be changing things up a little bit. There's no chalk, there's no board, it's all virtual. And we're going to try to maintain the same level of participation. And to do that, we've introduced a few different things. So first, if you're a student in the class, you've been sent your assignment to the new company we have founded called Very Therapeutics. And you will either be a medicinal chemist, a process chemist, or a radiochemist within that class, which means you'll have to master the retrosynthetic skills of each of those types of chemists. And participation is going to be encouraged through the mining of a new crypto or chemocurrency called Pyridone. And so Pyridone is a useful currency to get points on the exam, transfer to current students that your friends, or you can even gift them to future people who will take the class on their own. Pyridone can be used in a myriad of ways, including points on the final exam. If you become a Pyridone millionaire, it's conceivable that you wouldn't even have to take the exam. You could just use all your Doge credits. You can also use it for swag. So like yogurt here from Spaceballs, you can buy some merchandise that will be coming soon, t-shirts. And unfortunately, we're not allowed to sell flamethrowers, or we would do that. But so that's how we're going to try to get people to talk. I'll call on people a lot. You're encouraged to participate and just come in and unmute yourself whenever you have a question. For the many people that are taking the class sort of as outsiders, you can also ask questions through the Q&A box, which I will not monitor, but Tucker and Max here are amazing TAs. We'll be filtering those questions, answering some of them, and then the ones that are particularly relevant to the class, putting them to my attention, and we'll address them in front of everybody. Now, some procedural issues regarding the midterm and the final. That is, as usual, an open notes exam. It'll be proctored over Zoom, and you'll be allowed to use anything you've written down yourself, along with the essentials. So you've been given these PDFs. Even if you're an outside person, these have been sent to you. So these essentials of heterocyclic chemistry, you can print these out and you can use them on the exams without a problem. And anything you write. So if you want to take the Jewell and Mills book and write it yourself out, all 1,000 pages of it, or take the Portable Chemist Consultant and write all 1,000 pages of that out with handwriting, you're welcome to use that during the exam. And let's see, is there any other issue we have to talk about before we start? I think that pretty much covers it. Now, as far as the textbooks, Jewell and Mills is a good one. But the Portable Chemist Consultant was written with the idea that if you really needed a fast way to grasp the information, you know, this would be a way to digest it very quickly. So it's kind of like it's written. I mean, it was written, I don't know how many years ago, 7, 8 years ago. Yeah, it's funny. My son actually on Friday, he says, "Daddy, you're almost 100, right?" And I was like, "No." And he goes, "Well, 40, 50, 60, 70, 80, 90, 100. So it's basically the same, right? You're almost there." So yeah, almost 10 years ago, we wrote this book with the idea of putting me out of business, so I wouldn't need to spend time consulting anymore. That didn't work, but nevertheless, the book is a really fast way of grasping how to make heterocycles and how to substitute them. So you'll notice every chapter in the book is written from the standpoint of how do you substitute a pre-existing heterocycle and how do you make it. And that really is a great introduction to the first 3 lectures. So the first 3 lectures are going to be kind of basic. It will be some complex issues incorporated into there, but these are the things you need to know before you can make the heterocycles. You got to understand how to functionalize them. So once you make them, or in some cases you'll be able to buy them, what can you do with them? And so each of these sections is divided between substitution, which basically is simply a way of saying reactivity, and then synthesis, which is the basic sort of retrosynthetic analyses of how you go about putting these things together. And then retrosynthetic analysis in this course will be taught from the vantage point of 3 different types of people: the medicinal chemists, the process chemists, and the radiochemists. And as you'll see throughout this class, the way that they think is very, very different. And hopefully you'll understand soon why a process chemist route to a molecule is not necessarily better than a medicinal chemist route, and vice versa. So with that, let's begin with general reactivity 1. Now, in general, if you want to get into the world of heterocycles, you've got to do something very simple, which is you've got to take an aromatic ring and you've got to take one of those carbon atoms and substitute it for a nitrogen. And if you do that, you're going to get an electron deficient heterocycle that has, it's like pyridine type. And it's important to remember that a pyridine type nitrogen is very, very different than a pyrrole type nitrogen. So a pyridine type nitrogen basically is like 3 different things in one. It's a schizophrenic heterocycle. So within it, it reacts like triethylamine. It forms various adducts, obviously. It reacts like nitrobenzene. So if you look at the electrostatic map at the last section of the PCC book, you'll see electrostatic maps of all the heterocycles. You'll notice the effect of pyridine renders it very similar to the effect of nitrobenzene on the neighboring carbons in terms of its ability to do something like electrophilic aromatic substitution. And then finally, the pyridine-like nitrogen gives that heterocycle an imine-like reactivity. So it's an imine, it's triethylamine, it's nitrobenzene, all in the same heterocycle. And these effects are additive. So it works on pyridine, but it works whenever you see a pyridine-like nitrogen that's embedded into a heterocycle. We're going to get into some very, very complicated heterocycles. By the time we get to lecture 15, 16, whatever, we'll look back on lecture 1 and laugh at how simple we were looking at. But all the concepts I'll keep bringing up over and over again. All the problems of the day, I'll say, remember lecture 1, remember lecture 2. They were simple, but if you didn't master it, you have sort of no idea about reactivity. Now, if we take a carbon atom and we excise the carbon atom completely, and then we put a nitrogen in there, now what happens is you get a pyrrole-like nitrogen. So if it's an oxygen, it's obviously a furan, sulfur, thiophene, and we generally call these types of nitrogens pi excessive, meaning that although they're still aromatic, they have a strong desire. They're not really happy. You know, pyridines are pretty happy. You know, pyridine solvent, you know, no problem. Everybody uses it. It's very happy, stable, aromatic. Whereas pyrrole, not so happy. They're generally just unhappy with life, and they're just constantly trying to do something. And these pi excessive heterocycles, in the case of something like pyrrole, have a strong inclination to start doing things like that. So they desperately want to attack something. Whereas pyridine is pretty content. Although its nitrogen atom can be somewhat ornery and can stick to silica gel and it can attack an electrophile, it pretty much stays put, and you can protonate it, deprotonate it just fine. But a pyrrole is not so happy. Now, it's really important to understand aromaticity and try to categorize in your head a general way of thinking about aromaticity so that when you see a heterocycle, you can recognize the aromatic parts and the less aromatic parts. And in order to help you with this, we've got in the Essentials PDF a kind of vague overview that shows kind of some heterocyclic aromaticity values that are kind of vague, but in general, the order here is accurate, showing the most aromatic, something like pyridine, going back to something which is not very aromatic, like isobenzofuran, where you've got you know, something which desperately wants to react with anything. Now, it's really important to understand aromaticity for a variety of reasons. It will guide you in the way you think about reactivity. So often medicinal chemists will propose heterocycles in a consulting session that simply you know, would be interesting ones to think about in theory, but have no basis in reality, and you would never want to give it as an actual drug because it's inherently not so stable. So knowing what will make a compound more aromatic helps you think about its reactivity and stability. And then there's tautomerism, which we'll talk about in a little bit later in today's lecture, which thinks about where is the proton. That kind of matters, where the proton is. If you're a medicinal chemist, it matters because you need to know how it's going to dock into an enzyme pocket, whether it's going to be a hydrogen bond donor or hydrogen bond acceptor. If you're a process chemist, it kind of matters because maybe you want to alkylate one of the nitrogens, and you need to understand what the dominant tautomeric form, where the hydrogen is going to be, which nitrogens are going to be pyridine-like, which nitrogens are going to be pyrrole-like. All of that is determined by tautomerism, and all of that can be traced back to the qualitative guide of aromaticity. Substituent reactivity, we're going to talk about this a lot. So the effect of the aromatic nature of the heterocycle controls the reactivity of neighboring things like methyl groups or carboxy groups or hydroxy or amino groups. Like how do those functional groups react? It all goes back to aromaticity. And then finally, as we'll see when we start thinking about how we make molecules, it helps you think about retrosynthesis. So when you're talking about bridged heterocycles that have two heterocycles within each other, how do you know which ring to break first? Something we're going to talk about a lot in this class. And again, aromaticity is a useful way of thinking about which one do I buy, which one do I make, which one do I annulate. All of that comes back from getting that sort of intuitive sense of what is more aromatic than another one. Okay, so with that, let's go to problem of the day number 1. And this concept here, that the tendency to give addition rather than substitution increases as the aromaticity decreases, is well illustrated with the classic case of how you make 3-bromopyridine. And so this looks like a good problem for a process chemist. And luckily we have several of them here. So maybe Jun Chen, who's a member of the process team here at Very Therapeutics, can help us with what is going on here. What is oleum? What the first step might be? There's no wrong answers. Whatever you say, I can turn into something useful. So just say something. It can be even how your Easter Sunday was. I'll turn it into something. So okay. Jun Chen, go ahead.
Okay, so the first reaction.
Oh, I can't hear you. Can you go ahead? Say it again.
You can hear me?
Yeah, I can hear you now. Yeah, perfect. Yep.
Yeah, the pyridine first has a lone pair and then react with SO3. Will give you a dot.
Okay, now what do I do?
Now then react with bromine.
Where?
This double bond, I would say.
I put some numbers to help me out.
Oh, 2 and we'll react at 2, 3, C2 and 3, 3.
So tell me, in a compound like this, that's a good thought. Let's look at 2, 3, and let's think that you know, in the sort of, let's just draw the resonance form of this one. Which one do you think has the highest electron density? Remember, over here, I said I want you to think like pyridine is an imine. So that would suggest to me, Jun Chen, that this 2 position would be pretty deactivated. Don't you think?
Yeah, I agree.
You agree. Good. So I would say we're not going to touch anything around 2. So why don't we move over 1? Wouldn't you think?
You can put the positive on C3, C4, and then you will get something like enamine.
Okay, so let's do that. What we're going to do here is we're just going to do a classic. We're just going to pretend it's an olefin, and we're just going to add in bromine.
Yeah.
All right, great. Now I've got to make some choices. I've got hydrogens there, and I need to somehow get back to the product of 3-bromopyridine. So how am I going to do that? If I eliminate one of these protons, I'm going to get 3-bromopyridine, but if I eliminate the other one, I'm going to get 4-bromopyridine, which is not the answer. So how do we rationalize there's a selective deprotonation that takes place between one of these hydrogens that leads to the product and one of these ones that does not? What do you say, Jun Chen? Any ideas?
Yeah, as you mentioned before, we can treat this guy as a imine, and if this double bond is a part of imine, this hydrogen is more acidic than the para one.
And this is the more acidic one. We're going to eliminate that, and that's going to give us our product after workup. Great. Well, Jun Chen, the first answer of a question in heterocycles, that's probably worth a cool 5 Pyridone, don't you think? Yeah. All right, great. So he's currently the leader. Great. Now let's take a look in contrast. Indole can be brominated. This takes place probably as low as -30, -40. And in this case, we're actually using pyridine-based brominating agent. So pyridinium trihydrobromide is a nice, popular, happy brominating agent. It's stable as an adduct with bromine in the form of this trihydrobromide. And that can be used very easily to brominate indole. Now, the site of bromination is at C3, which follows the rules of reactivity that you would expect. If you did this on pyrrole, what do you think would happen, Nathan, who is a medicinal chemist at Very Therapeutics?
I think it would attack at C2 doing an electrophilic aromatic substitution.
Perfect, fantastic. So this one takes place at C3. The question I get every year is, why is that? And the way to think about it is that because you've got this benzene here, you have effectively made this compound much more unlikely to disrupt that neighboring aromaticity. In this case, we have a movement of electrons that looks like that to give you higher degree of C2 reactivity. If you were to do the same thing on indole, it would require that you disrupt the aromatic core, and that's why that doesn't happen, and that's why all substitution at indole will in fact take place at C3, not at C2. Any questions on that? Now, people, yeah, go ahead, Brennan. Yeah.
So when you brominate the pyrrole like that, how much harder is it to do another electrophilic attack? I mean, how
Not hard at all. Not hard at all.
Okay.
In fact, pyrrole has a lot of juice in it. So if you wanted to do another reaction on this one, you could. And but you raise a good point there, Brennan. So what if I want to get C3 bromination? Is there a strategy you might think that we could use for that? How would you conceptually think about doing it?
I mean, you would have to put some blocking groups maybe.
Awesome, awesome. And the blocking group that people usually use is a TIPS. In fact, this group is so popular that it actually is a part of the chapter on pyrrole. So if you take a look at the pyrrole substitution starbursts and examples, take a look at the right-hand side, folks. It's all about TIPS pyrrole, which was introduced by a famous medicinal chemist by the name of Joe Muhowski during the synthesis of ketorolac, which we'll talk about, I guess, next week. But a very useful way of changing the site of reactivity on a pyrrole just by blocking that group. Wonderful. Thanks, Brennan. A few pyridoge coming your way. Check your account. All right. So generally, people are not going to want to put an indole into their medicinally important compound. I rarely see people just take a regular indole, and you may say, hey, what about tryptophan that's in our body, everything, but rarely are small molecules with an indole progress to the clinic without doing something to them to attenuate the reactivity of the C2-3 pi bond. So generally, there's an electron withdrawing group, or they make an indazole instead of indole, or they make a benzimidazole. They do something, or they even take this and turn it into an azindole, as we'll talk about later. So the reason for that is, of course, you want to tone down this reactivity, take electrons out, and turn it into something which is actually going to be stable in the body. All right, so more on how aromaticity will dictate how things react. Cyclic transition state reactions, specifically paracyclic reactions, they increase as aromaticity decreases. And this makes intuitive sense. It should make intuitive sense to you, right? I mean, you can't do Diels-Alder with pyridine, just like you can't do Diels-Alder with benzene very easily, unless you have some sort of excited form of it. It's pretty rare to do something like that. So whereas things like pyrrole, if you take a pyrrole, for instance, and you throw a Bach on it, that will then do a Diels-Alder with that, no problem. Same thing with furan. Furan, you just heat up that with acetylene dicarboxylate, and you'll get out your product with loss of ethylene, and the product of that reaction will be that. I'm always going to abbreviate in this class esters with the E. That's what that means. So if you take furan, you heat it up with this compound, you get the initial adduct, and then minus ethylene gas, and you get out that product. So it's not very aromatic, and it has no problem acting like it's not. But it is aromatic. It's just not very aromatic. Okay. Probably the most important, well, one of the most important things when you think about aromaticity is thinking about how aromaticity will affect your tautomeric state. That is, where is the proton? And so in the case of something, let's go through each one of them. If we have, for instance, Pyridone. Oh, sorry. So Pyridone can be thought of as a few different forms. We can have this form. We can imagine that the proton is here. And we can imagine it's like that. So which form is the most important form here? Maybe a radiochemist like Tim can help us out.
I think that the first structure you drew would be the dominant tautomeric form.
Is it aromatic?
Yes.
Okay, great. So all of those are sp2. It is aromatic. It has great stabilization because of the CO double bond. That's a huge stabilization. There's probably also some hydrogen bond action going on. So in solution, it's going to be 99% that. Only a little bit of this one here. But it helps you to understand what the different tautomeric forms are, because when you treat a compound like this with a halogenating agent, it's very easy to rationalize the halogenation selectivity by imagining this tautomeric form. Now let's take a look at the case of Aminopyridine. So Tim, using your logic, I'm going to predict that this one is the dominant tautomeric form. Is that right?
I don't think so. I think
You
it
don't
would
think so?
be the right one. Yes.
Well, which one do you think it is?
The right one.
The right one, exactly. So in the case of aminopyridine, it's the dominant tautomeric form. 99% is going to be the aminopyridine, and just a little bit is going to be that Aminopyridone. So understanding all the tautomeric structures that you have in a heterocycle is key, and it can play an important role even in how you design a medicine. So for example, in this problem, that was pretty much when this class first started back in the early 2000s, this was a topic of great interest, which was the upheaval of the pharmaceutical industry by the removal of Merck from the market of this very efficacious COX-2 inhibitor, Vioxx. And you may have grandparents that took this compound. It was a really good pain reliever for arthritis, and people shifted now everything to Celebrex from Vioxx, but it was a very low dose compound, and Merck got in trouble when they started increasing the dose tremendously, and then there were some real big tox problems. Now, as a medicinal chemist in the modern era, when you look at a compound like this, and maybe we'll pick on Brendan again just because he has worked on compounds like this in the lab, what do you think might be a potential problem with employing a butenolide like this in a medicinal chemistry context? You can tell us whatever you're thinking.
Yeah, no, I'm aware of this because I remember looking at this when I was working on the butenolide stuff. So yeah, that CH2 is really hot. Yeah, under biological conditions, it's probably going to get deprotonated, and then oxygen around, it's going to get oxidized, and then now you have a super hyper electrophile that can be a nice alkylating agent.
So if you just understood the possible tautomeric form of a 2-hydroxyfuran, and the realization that that is a potential intermediate one can get that then renders that CH2 kind of acidic, and then thinking about what this compound would do as a very, very pi excessive heterocycle, you could rationalize, as Brendan says, that reaction with triplet oxygen would give you this hydroperoxy intermediate. And that hydroperoxy intermediate has two choices. It can either disproportionate to give the hydroxy compound shown here or the maleic anhydride compound shown here through a Russell type mechanism. And the problem with this one is you've got a latent aldehyde. And the problem with this one is now you have a maleic anhydride, which is a phenomenal covalent reactive group. So the jury is out as to whether this is the reason high doses of Vioxx are toxic, but from a heterocyclic chemistry lesson, it's probably a butenolate is something you'd want to really carefully de-risk as a lead candidate before putting that into the clinic. Is there a really fast way that anyone can think of putting this thing together? Maybe we need maybe a good process chemist like Carter could help us out in terms of how you would think about just putting this together really quickly. Is there a bond that you could potentially break that would make it really, really fast to put it together?
3 and 4.
Oh, yeah, brilliant. So breaking that thing up, our first ring synthesis example. So just mixing those things together, you'll get a O-alkylation and then an intramolecular aldol to do exactly what Carter told us. So thank you. All right, I see this problem come up sometimes in medicinal chemistry consulting sessions. People will ask for things like that. So the 2-amidofuran. What do you say, Tiffany? Can you give us some thoughts on this problem of the day? How would you put it together? And what would you tell the medicinal chemists?
Can you just block protect the immune? I'm not
Oh,
sure.
I'm so happy that you said that. You made this lecture so much better. Awesome. That's great. So we're just going to take 2-aminofuran and Bach protected. Everybody good with that? Everyone's good with that.
That compound is
Oh, who's saying? Oh, sorry.
It's me.
Who's that?
Nguyen.
I can barely hear you. Who is it?
Nguyen.
Nguyen. No, okay, go
Yeah.
ahead, Nguyen. What are you saying? What's the problem with this?
No, just like that compound is too electron rich, and like I'm not sure if you can. I mean, you can just isolate it for the reaction.
Yeah, that's right. So this compound, please don't ever propose compounds like this with this group being X here and anything here. Doesn't matter what you've got here. Pretty much the only way this compound would ever be stable is if there's a electron withdrawing group here. Then sometimes you can propose that sometimes, but in general, amidofurans, amino-indoles, amino-indoles, aminofurans, aminopyroles, don't ever propose them. They're going to be instantaneously react with oxygen. They won't last for more than a minute, and this thing will likely just lose ammonia and give you butenolide if you're lucky, but probably just give a polymeric mess. But your job as a consultant is never to question what the medicinal or process chemist wouldn't ask this question, but a medicinal chemist would ask something like this. You never question what compound they want to make, or you'll never be hired again. So I need to make this compound. How am I going to do it?
Can we start from acid or aldehyde?
Aha. So if I start from an acid, what reaction do you want to do?
Yeah, I don't remember many name reactions. It's a Curtis reaction or?
Brilliant. So we just take the commercially available and available from furfural. 2-feroic acid is one of the cheapest commodity chemicals you can find. And that's how you're going to get your NH-Bach there. Just do a courteous. And that's one of the tricks I often use for these rare occasions where someone will ask for a heterocycle that I know will never be part of their drug, but they still insist on getting a route to it. Okay, great. So understanding tautomeric forms leads us into one of the most popular consulting questions that arises, which is regioselective alkylation and acylation. This is a problem which comes up a lot. It's probably like 8 or 10% of the problems I've seen is people struggling with the issue of how to get an R group on a heterocycle in the proper orientation. So for exhibiting this aspect of tautomerism, let's take a look at the isoxazolone shown here. And perhaps Stone can help us out in thinking about, first, what are the two tautomeric forms? And then after we talk about the tautomeric forms, which one potentially plays a role in getting either of these two adducts? So I'll make it easy for you to participate by labeling these so you can talk to us about what the tautomeric forms might be. So Stone, what are you thinking?
I summarize 3, 4, and the carbonyl to the enol.
Nice. Okay, that's one. And how about another one?
And I guess you could have the zwitterion.
Well, I'm going to give you a little clue here. You've got these two hydrogens here. I mean, you could, in fact, think about it. You're not wrong. You certainly could keep doing that. Yep. But there's something else.
Oh, sorry. Have the 2,3 double bond.
Brilliant. Okay. Now, so Stone, let's keep going on this one. We're going to label them A, B, and C, and D. Which of these is not aromatic?
The one we started from.
Brilliant. So not aromatic. So we should still remember it as a potential tautomer, but recognize it's likely not going to be a dominant tautomer when we think about reactivity. So that gets us to problem of the day number 3, which Stone, you can continue on, or you can recruit help from your neighboring radiochemist Camille, who I know also wants to help here. And so we're going to take that isoxazolone, and we're going to either treat it with base and benzoyl chloride, or we're going to treat it with acetic anhydride and heat. And so need to have some way to rationalize what's going on here. Which product do you think we might get? We can get, if you think about it, we can get alkylation or acylation here, here, or here. Maybe even one could propose here. So where is it going to go? How about let's tackle the first one, benzoyl chloride and sodium hydroxide. To save time, I'll draw the 5-member ring.
I think first you're going to deprotonate.
All right, so we're going to deprotonate, resulting in what kind of adduct? It's going to go at oxygen, carbon, or nitrogen, do you think?
Resulting in an adduct at oxygen.
Brilliant. Awesome. And now if we take that compound and we treat it with acetic anhydride and just heat it up, neutral conditions, what is going to be the product, do you think?
The nitrogen is going to react first.
Why did you say that? What made you say that?
It's a pyridine like nitrogen.
Oh, that's so great. Every year the students get better and better. So quickly they pick up on it. Awesome. Yeah, that's exactly right. So when you're thinking about these conditions of how do you control regiochemistry, you're always going to be looking for the pyridine atom, and you're going to be looking for the pyrrole atom. And that's going to result in some pyridose coming your way for sure. 5 more for you. Great. Let's talk.
There was a typo on the biopsy sample.
Oh, there's a typo in the biopsy sample? Sorry. What is the typo?
So your retro, you have phenylcetic acid as opposed to the.
Oh, yeah. Sorry. Thanks. There you go. Sorry about that. Thank you.
Phil.
Yeah.
If you do benzylation on one of those tautomeric forms, would you see a mixture of
If you do
benzylation
what?
and
If you do benzyl chloride, for instance?
right? Yeah.
Yes, you would. It would depend on, and we're going to talk about this a lot in a moment, but in general, you're going to have a few options for making selectively, let's say if you wanted to address your question, make that compound versus that compound. And the things you would do would be, you'd have a few strategies that we'll talk about later, but so let's revisit this question. It's a good one. Is that Nick?
Yeah, it's me.
Yeah. Nick, we're going to get into that in just a moment. Of the strategies one will use when you're confronted with this problem. So stay tuned. I'm going to return to your question.
Okay, sure. Yeah, thanks.
Okay.
Yeah, I had another quick one.
Sure,
If that's okay. When we compare the pyridone with the other form, so what about a thiopyridone? Well, it would be like a pyridothione. Is there a way to shift the equilibrium into the thione form?
Well, for all intents and purposes, and when you see this, this is commonly probably the most common application of this is when you see it in the case of the Barton type decarboxylations. Usually there's an N-hydroxy here of this type. For all intents and purposes, the reactivity of this is going to be always at sulfur. So whether it's reacting in this form or in this form, electrophiles are always going to react here. And I guess your question is, how do I get N reactivity instead of sulfur? Is that right?
Yeah, right. If say I wanted to benzylate at N, or if I wanted the N to be deprotonated.
Oh, that's a great question. I'm so happy you asked that question. So let's take this, and the first thing I would do, if this was a consulting question, I would say, hey, what you'll need to do is convert that to S-methyl, turn it into a pyridine. Now I've got a pyridine, right? Watch what happens. Watch what happens. I'm going to treat this with benzyl bromide or benzyl chloride, and it's going to do this. How do you like that?
Right. So it's basically you protect first, then you do like an SN2 that deprotects it.
Correct. You've got to shield it, and then you can get the reactivity you want, because it's unfortunately not that easy. And there may be some random paper you can find out there, but not, I don't know it off the top of my head, a way to stop sulfur from reacting with an electrophile. You've got to protect it and then make the pyridinium, and then that should spontaneously demethylate, giving you methyl bromide and your desired product.
Right. I see. Yeah. Thanks.
Yeah.
Phil.
Great question. That's awesome.
Just a quick question regarding that. So, like, can you like selectively methylate the sulfur over the nitrogen?
That's what's going to happen.
Okay.
Automatically.
Okay.
That's the first thing that's going to happen. So when I treat this with methyl iodide or whatever methyl triflate, whatever your favorite methylating agent is, you're only going to get that very quickly. Low temperature, instant.
Okay. Thank you.
Yep. Okay, super. Now, this is an interesting one to mention. Many of you are probably going to end up in the pharma sector, and you might want a little bit of history. This was first made in 1884 by Ludwig Knorr of the famous Knorr reaction that we'll talk about next week. It's the first synthetic pharmaceutical agent that I'm aware of, and it was marketed by Sandoz. Antipyrine, it was to lower fevers if you had a fever. And This was made by simple methylation. And we can probably rationalize how to make our very first pyrazolone by using simple disconnection logic. So how about Kelly help us out with how you would just put this together in one pot really quickly?
Can you make it from phenylhydrazine and methyl acetoacetate?
Brilliant. So we're just going to take that. So Pyridone is being deposited into your account. And there we go. Brilliant. Okay, let's take a look at some other tautomeric quagmires and think about which tautomeric form these might reside in. And so for this one, maybe Daniel over in Florida, a process chemist at Very Therapeutics, can help us with this first one. Based on what we've talked about already, what do you suspect is a dominant tautomeric form here, A or B? What do you say, Dan? And is Dan on the line? And if Dan is not on the line, luckily Taiwei is going to help us out. So many chances for Pyridone. How about Alex?
So your dominant form will be B because you have the opportunity for H bonding in that form.
That's strange. I mean, I also have opportunity for hydrogen bonding in this compound, but yet everybody was adamant that 2-aminopyridine is going to be in the form of the amino tautomer. And I believe that was Tim who insisted upon that. So Tim, are you in agreement with Alex?
Yes.
Does anybody think A is the right answer?
Do you think it could be depending on the solvent? If, for example, the H bonding is attenuated in a way that could become actually a dominant form?
That would be a way of thinking about how you might be able to control selectivity in terms of alkylation. But what Alex said is actually right. In this case, it is very, very dominant form to the extent that it's the major one you're going to see in terms of reactivity in solution for precisely the reasons she mentioned, which is hydrogen bonding effects. So in a case like this, the more nitrogen atoms you add to a heterocycle, the less aromatic it is. And so the penalty you pay is actually very low. Anyway, this compound is still aromatic, and you've got the bonus of hydrogen bonding effects. But maybe the situation changes here, Alex. Do you still want to do the same thing and select B, or are you going to finally go with A?
I think B is still more dominant for the same reason.
Anybody want to disagree with her?
So I will say, like, when you first look at these two forms, the first one feels more correct, just because when you see the exocyclic olefin or the exocyclic imine like that, it just doesn't feel right. But then you consider, yeah, the higher level effects that might be happening in a flask or in solvent, and that might push you to think that maybe, yeah, the hydrogen bonding is a little more of a stronger force here.
Yes.
Especially because, like, I imagine what life would look like if, those tautomeric forms were in the enol form and not the form that can H bond. And I wonder what would happen to our DNA and things like that. So
well, you'll find out in a minute. We're actually going to cover that, Brendan. But that's a great point. And so again, in both cases, B is the right answer. So the take-home lesson here is, remember, the more nitrogens you put into a ring, the less aromatic it becomes. Other effects become dominant, and one of those is hydrogen bonding that can direct the tautomeric equilibrium to the one shown there. Another case of aromaticity driving you to important directions is thinking about patent law. So I've seen cases where folks will put the wrong tautomer in their patent, in their structure. We probably have people on the line in the outside room that write patents all day. So if you are putting the wrong form, tautomeric form, you open yourselves up to potential litigation with folks saying, oh, it's not the same compound, they didn't know what they had, and generic cases have been tried with very, very similar types of situations. So it might seem frivolous to you, but it's kind of important to know what tautomeric form your API is in. Let's take a look at the effect of hydrogen bonding, as Alex brought to our attention here, and how it can impact tautomeric forms of substituents on a heterocycle. So for example, if we have a pyrazine or a pyridine, such as A, and we've got a ketone that's adjacent to it, what do you think is going to be the effect of the tautomeric equilibrium? Is it going to reside as compound B, or will it just stay in the form of compound A? Maybe Nguyen or Carter, whoever wants to jump in first.
Seems like B would be the correct one based on what we've been talking about.
Yeah, B would be the right one. But let's take it a step further, since you volunteered. What happens when I now benzanulate in the case of C? So if I've got a quinoxylane or a quinoline, what happens then?
I think still the nitrogen would be available for hydrogen bonding. And even though it wouldn't disrupt the aromaticity of the appended ring.
Yeah, that's true. However, in the case of C, the dominant form, when you start putting a benzanulation on there, it is in the form of C, not in the form of the enol form. And so, but your point is a good one, and this compound is still very acidic. So this is kind of like a malonate proton, very, very acidic, because remember, as we talked about before, you got a pyridine like nitrogen, that's like an imine. So this, to me, looks the same as dimethyl malonate in terms of reactivity. Now we get to Brendan's question of, he thinks it would, this type of tautomeric situation has a lot of impact on, potentially our evolution. And it turns out that the reason we're doing this class over Zoom and we're not just climbing trees and eating small fruits and little monkeys is because of this phenomenon. So Tautomerism is the reason you're here and the reason we're doing this with an iPad. And normally the DNA bases like to sort of get together ATGC, we know that. So adenine and thymine have a nice complementary hydrogen bond donor, hydrogen bond acceptor, forms the basis of the DNA double strand, keeps them together really nice and tight. However, something can go wrong when cytosine starts masquerading as thymine, because cytosine can sometimes be in this tautomeric form. And now you can imagine you can have a hydrogen bond acceptor here and a hydrogen bond donor here. And so C can sometimes couple with A. And such types of mutations are what happen in evolution. And that's what sort of drives, I guess, a lot of evolution. It's just one of the facets of it is this tautomeric form of cytosine that steps in for thymine on occasion. And that's how you get random mutations. There's a question from the chat. So what is that?
So Colton Johnson wants to know how relevant is bond strength are.
Well, how relevant is the bond strength argument when determining tautomeric form? It is very relevant. It's kind of like the same, for the same reason that you can go, everything I'm talking to you about, you can go back to frontier orbitals and rationalize it out. The point of this class is so that you don't have to necessarily do that rationalization. But if you want to take it back to first principles, you certainly can. And so everything I'm saying has a strong basis in what you learned in PhysOrg, I guess. The pK of phenol is around 10. pK of aniline is around 35. It's easier to take phenol and do alkylations to the alpha position, that's known, but it's pretty much unheard of to do that here. And it has to do, again, with the bond strength argument that you can make for the OH bond here and the NH bond here. The same bond strength arguments can be made for determining tautomeric equilibrium, but all of that is directly proportional to, as well, the relative aromaticity. So these kind of ways of quickly ascertaining tautomeric equilibrium are a substitute for going to your DFT calculations and actually calculating BDEs. But you can do that if you want to. Great question. So tautomeric equilibrium can also be used to help you in terms of reactivity. So when I look at a isoquinolone like this, you can imagine this isoquinolone is very, very similar to a regular amide, or even looking at this as a carboxylic acid. So if you wanted to take a carboxylic acid and convert it into a derivative by loss of water, you could imagine doing that with a variety of different peptide coupling reagents. And one of the ones that you can use here is Pyridone. This is a very, very useful method for skipping the step that often people do, which is a POCl3 step, to convert that into a chloride. Instead, you can just do it in one pot and get your nucleophile added in there directly, as if it was a simple carboxylic acid. In fact, you can take such intermediates and even use them as surrogates for a halide in Suzuki cross-coupling. So this is a really useful set of conditions to remember, especially when, for instance, the rest of your molecule doesn't tolerate something like POCl3. This is a much more mild way of getting the job done. Okay.
Phil?
Yeah.
If I wanted to protect this kind of quinolone with this group, and then if I had halogen as well, and I wanted to do a Suzuki cross-coupling, would the halogen go first, or I couldn't use that as a protecting group?
What do you mean you want to, sorry, I don't get the question. So you want to convert it to POCl3, convert it?
Yeah, so if I reacted with the Pyridone,
okay.
And that had, say, a bromine in the 3 position or somewhere, and I wanted to do a Suzuki Suzuki.
You're asking what the relative reactivity is of that intermediate adduct versus a standard bromide. It's going to react kind of like a triflate, and so I would anticipate you could find conditions that would give you selectivity of the Pyridone activated. In this case, it's usually an HOAT type adduct. That you could get selectivity of, for sure, I bet you would get that selectivity of that coupling under the right conditions versus a bromide. It might be even easier to use a chloride, but I bet you could even get a difference between if you had the bromo here and you had the O activated group here. Is that your question?
Yes, yes. So the question is basically, could I use this Pyridone as a protecting group for oxygen, or that would go first?
Well, you wouldn't protect it. So you'd make this in situ. Nobody makes the adduct and then carries it forward in a subsequent step. It's not stable. So you activate it in situ and then you do your Suzuki.
Right. Yeah, yeah. What I mean is if I wanted to do a Suzuki on just a 3-bromoquinolone, normally it would have to be protected some way, either N-benzylated, or it would have to be an OPMD or some other protected group. So that's why I'm asking whether you could just protect it in oxygen and then do a Suzuki on the bromide. But you're saying basically it's going to go for the O.
I think the best way to achieve that, and that's a really good question, so we might as well take a sidebar. By the way, this year, I'm not under a time crunch to finish these lectures because much of the content, we've added a lot of new content, but a lot of it is also on YouTube. So if we don't finish the lecture in time because there's a lot of good questions, I'm not going to rush. You'll just have to finish the lecture yourself on YouTube if you're taking the class for a grade. So let's go through Nick's question. And he points out that when you do a standard Suzuki, the problem is these Suzuki conditions are rather basic. This is a great, I see this consulting problem all the time, this type of thing. You generate this anion and guess what? Oxidative addition is shut down. That's Nick's question. How do you do a Suzuki on that? So there's a few ways of thinking about it. One is to try to in situ protect as a TMS. I've seen people do that. They use usually bis trimethylsilyl acetamide. And that will instantly put a TMS group here. And that gives you a better chance of getting the coupling. Another way I've seen people do this is using anhydrous conditions that are less basic Suzuki conditions. Another way I've seen is people using additives like copper to chelate that nitrogen and thereby allowing for less of an equilibrium that lies less in the anionic side and more of an N metal, N copper That gets you oxidative addition here. Worst case scenario, if none of that works, as you said, you could throw a dimethoxybenzyl on there and then remove it upon workup with TFA. But that's a great point. And we're also going to talk a lot about, in this class, haloselectivity. So when you've got multiple halogens in a molecule, which ones react first?
Yeah, I'm asking this because the ligands that I make, the pyridone ligands, I always had to protect the oxygen first. You use a PMB or a TSE protection group and then do a Suzuki. So normally they work with it's a much lower yield if it's an unprotected quinolone or
That's right.
pyridone.
And that's the reason why. Yeah.
Okay, thanks.
Yep, great question. You know, the facility of, just as the facility of pericyclic reactions increases as aromaticity decreases, the same thing for strange little rearrangements like this one that can be quite useful. In this case, we take we see an isoxazolone. We treat this compound with either heat or light, whatever your favorite conditions are, and out pops an oxazole from this. So can someone rationalize what might be a step? Maybe Aaron could tell us anything about this compound, what he suspects happens when you just heat this thing up? Or light?
It looks like it's a decarboxylation.
Oh, brilliant. That is great. So if we do a decarboxylation, I'm just sort of abbreviate it like that. That's going to give us basically R1 here, R2, eraser. With a carbene, which you can also, if you don't like to think about carbenes in your mechanism, a little trick to use is a plus minus there, and then cyclization and tautomerization, and there's your product.
Just in thinking about this mechanism, I had drawn it where you like have stepwise cleavage of the NO bond and then decarboxylation.
Yeah, we can certainly do that too if you like. So if you want to go through sort of more of a radical-like mechanism, you can imagine that you get an intermediate like that. And then we can do the whole sequence of events in the same way. So that rate of decarboxylation should be high. And then that diradical will then cyclize via going here, here, here. Is that what you had, Alex?
Yeah, essentially.
Yeah, that's fine too. Either mechanism is fine. But remember, the key message from this is that although this isoxazolone is aromatic, it's barely aromatic, right? It's kind of like, yeah, I'm aromatic, but I'm not too happy. So you heat me up or you shine light on me, and I'll very happily liberate CO2 to become something which is more aromatic, which in this case is an oxazole. Great. Let's talk about the effect of different types of nitrogens on attack with electrophiles. So this is really important. And again, these are the sort of constituent parts of complicated heterocycles. So I've seen this in exams. It is maddening. Just remember this. If you have a pyrrole and you deprotonate it, that is wicked reactive. It will alkylate really, really well. It will react at nitrogen. If you have a pyrrole that has an R group on it, this lone pair will not attack anything. Don't do that in a test. Don't propose it, please. They don't attack anything. They're always going to attack at carbon. Nitrogen atoms and pyridines, obviously, really, really high reactivity. And if you have a beryllium or a pyridinium, do not try to attack. It's all dead. It's pretty much nothing left there. The nitrogen can't do any more attacking. So with that in mind, when we treat pyridine with acetyl chloride and methanol, two types of esters arise as the product. And luckily we have some volunteers to help us with this one. They can speak up now or I can call on them. How about Ellie? what is the first elementary step, do you think, of treating pyridine with acetyl chloride?
Will you like acetylate the nitrogen?
Oh, that's
Or
great.
like,
Wonderful. Great. Now what do I do?
you can attack with the like methoxide or with methanol.
All right, awesome. Where do I attack?
At the carbonyl carbon.
That cleanly gets me back to my product, starting material, sorry. Great. And that gives us methyl acetate and starting material, which means we need to do something different. Because certainly I wasn't asking you to turn pyridine back to pyridine. So let's think about what else this can do.
Maybe attack at like the 2 position, the methoxide.
Right. Great, let's think about that. Okay, now what's that going to do? Oh, I should draw it like that. There you go. I'll give you a hint. There you go. That's the great hint.
Okay, so you enolize.
Now what do I do? There's a new nucleophile in town.
Okay, so you can attack another acetyl chloride.
Okay, but product is going to have 2 different esters. And I still haven't made even one. So what else can I do? You've identified this as an electrophile. Are there any other electrophiles that you've generated before and previously drawn on this screen? I'll give you a nice hint.
Oh, so the 2 position of the alkylated pyridine.
And then what happens to that? All I need is one more step I need, and I can turn this into an ester.
Methanol attacks at the carbonyl.
And I said there are 2 products. You identified the one arising from a C2 attack. Is there another position that I can attack?
Yeah, the C4.
Chapter hydrolysis. Give us that. Brilliant. Tons of pyridose coming your way. That was great. So that's why when people do Rysert type reactions or when they alkylate at C2, you use something like CBZ chloride or benzoyl chloride. You don't use acetyl chloride because then this mischief can go on. That makes sense? Let's get into the, and maybe for the, we tried to install, because we knew we'd have so many outside folks that were in companies, and lecture 1, 2, and 3 is often difficult for these outside folks because often they know a lot of this stuff. So we tried in each of these lectures to put what I call a little consulting corner, which is to encompass what is a very large proportion of the questions that I get, which is the curious case of imidazole. But furthermore, it applies to a lot of other heterocycles as well. So when you treat a imidazole with an electrophile, there's 2 different nitrogens that are hiding in there. Obviously, we have a pyridine-like nitrogen here, but we also have a pyro-like nitrogen here. And so if there's an electrophile with no base whatsoever, what do you think their Debbie, is going to happen?
Well, it's going to react with the pyridine type nitrogen.
That sounds good to me. Oops. And following the loss of a proton, you'll get out your product. Now, if we treat this compound with base, we will obviously form that. But the problem with this is it's called a mesomeric anion. And mesomeric anions are a disaster for medicinal chemists because they provide regioselective quagmires. So when you alkylate a system like this, you can't get any control. You end up with a mixture. You often only want one. Obviously, they're going to represent themselves in space very, very differently when you have R groups here. And so that's a big, big problem for imidazole, for pyrazole, all sorts of systems. So let's think about ways we can solve this problem. One way of doing this is through electronic bias. So if you take an imidazole and you bias it in such a way that there is, let's say, a halogen atom, we'll put an X here where X can be equal to chloro, bromo, iodo. And we treat this with sodium hydride and our electrophile, which is this, let's say, alkyl bromide or alkyl iodide. You get 100% control with only alkylation taking place here. And then you can do your Suzuki to get your product. So electronically biasing heterocycles is one way to do that. There are many, many examples of this in literature. For example, if you wanted to take triazole, how would you take triazole and alkylate it selectively here? Well, the answer is there's no good way to do that. So the solution to doing that was introduced by BI many years ago in an orglet. You can put 2 bromines here, same concept, and now the exclusive product is the one you want. So answer number 1 for how to control regioselectivity is electronic bias. So let's take a look at another consulting problem that comes up a lot, which is how do you alkylate a tetrazole? This one is tough because there's 2 possible ones that you can get, the one here or the one here. It's one of the unsolved problems of heterocyclic chemistry of how do you control which one you get. So in general, when I'm faced with a consulting problem like this, there are several things you can tell the practitioner. One of them is kind of obvious. Temperature, acid, base, and electrophile. Screen those. Sometimes you'll find that there's one idiosyncratic base in one type of solvent with a certain electrophile that just gives you amazing regioselectivity. And that comes from screening. It's a terrible consulting suggestion because they look at you like, you don't think we thought of that? So that's the first thing. You just make sure that they're thinking about that, and they're thinking about modulating the tautomeric forms they get. The next thing you can tell them is to use a blocking group, such as a trityl group. So that's where we get to steric blocking. So if you throw a trityl group on that, because of the repulsion between a trityl and whatever this R group is here, you can get selective reaction at the N2 position. And so if you have a big group at R, often you'll get alkylation away from that group. The final thing you can think about telling people is using neutral conditions for getting their alkylation to go, or acidic conditions to get it to go. And if none of those things work, you can tell them to just make the heterocycle from scratch. And that's why you need the other 19 lectures of the class. So we'll get into how to make all these heterocycles as regiochemically pure compounds that don't require an alkylation step. Well, there's another very popular trick that people use out there called the SEM trick. The SEM trick is a really nice one for basically taking an imidazole and making it do what you want, because you now have discrete control of the type of nitrogen atom in the ring. When we put a SEM group on the imidazole, we now have, in this case, something which looks like a CH bond adjacent to a pyrrole, which we'll learn tomorrow or on next week when we talk about CH deprotonation, makes this quite acidic towards deprotonation. When we then take this adduct and we treat it with catalytic SEM chloride, something really cool happens. And to help us with that, hopefully Alex can guide us.
So if after alkylation, if you add catalytic SEM chloride, you'll protect the other nitrogen, but that will also essentially activate, like make the other SEM group more labile. So that'll be removed, and yeah. And then that'll make the other nitrogen pyrrole-like, so you can alkylate there.
Why do you think this reaction works? What's driving it? Anyone?
Could be repulsion between the R group and the SEM group.
Yeah, exactly. So you're getting a thermodynamic outcome this way. And we'll see this a lot. This is a trick which is used quite a bit in companies in different manifestations.
And in the first step, so would you still get a bit of the alkylation between in the first step with butylithium or something? Would you still get installation of the SEM group at the 2 position?
No, in this case, this CH bond, as we'll talk about in a few days, that CH bond is more acidic than that one. If you did another alkylation, you could deprotonate there and put something else there. Where's the sneakers chemistry? Are we getting to that? What's that? It's what? Oh, I did? On that, and that's really good because we skipped over. Oh, yes, great. I'm so happy we skipped it over because now is the right time to talk about it. So let's talk about this case of azindole. This is a super popular heterocycle. As I mentioned to you before, indoles are very bad leads. They're good leads, but they're terrible drugs. You don't take a regular indole. You usually try to turn it into something like an azindole. So what based on everything we've been talking about now, what conditions would you use to get this product versus this product? And all we need is sort of the conceptual thought of what conditions you should be thinking about. Maybe we can, either someone can jump in and just volunteer, or we can go to maybe Sung Han in Florida.
So to generate the cup molecule, I would say use a basic condition.
What kind of base?
Sodium hydride.
Awesome. That will give you that very cleanly. And now Sung-Han, taking it further then, what would you do conceptually? What would you do to get the bottom one?
So for the bottom one, I think I would use neutral condition and treat them with the electrophile.
Brilliant. Now for bonus Doge coins. Sung-Han, how do I go from there to there? Anyone want to jump in for the save? That's worth at least a couple of Doge coins, I would say.
You just hit it up.
Well, you need something else. Remember the problem we just talked about with imidazole and SEM chloride. What did we do there?
Oh, you use the catalytic, the same reaction in catalytic amount and hit it up.
Brilliant. Lovely. So the reactivity of these two things is very different, and that will come into play when we talk in lecture 3 for how the differing ability to get these two outcomes just based on thinking about tautomerism can be usually beneficial when you think about how to functionalize different parts of this ring system. So very, very useful chemistry there that we will re-investigate in a future lecture. Let's get to a real world problem. JMed Chem problem here from pretty recent. You see these covalent reactor groups emerging as very popular chemotypes in medchem these days. And because it's a medchem paper, I'm going to make a disconnection for you that uses a simple Suzuki and gets us back to this compound. And then I need someone from the medicinal chemistry team to help us with a synthesis of this compound. Now notice, we haven't done imidazoles yet, so the answer I'm looking for is not an imidazole synthesis answer, but rather an imidazole substitution answer. So where are our medicinal chemists? We've got, let's see, how about Fang or Brittany? One of them? I don't know if they're on. They're auditing the class. Fang. Okay, Fang, any thoughts?
Me?
Yeah. Anything you want to say. It's fine. Now remember, the challenge here is I've got to find a way to put that methyl group on selectively.
Yeah, that's what I'm thinking about. But can you play the SEM trick again?
Oh, that's a great idea. Let's play the SEM trick again. If I played the SEM trick again, what would happen to this methyl group? What do I need to do to that methyl group to play the SEM? In other words, where do I put SEM?
So before you introduce the aromatic appendant or the bromide, you have to
The whole crux of the problem is how to get that right regiochemistry of that methyl group. I need it next to the aryl. And this bromine and this aryl, if I try to, let's say your suggestion was, can I just do this?
Of course not, because AR is obviously larger than bromide.
Right. So there's going to be an issue there. You'll probably definitely get a mixture of these two. So bad disconnection. So where am I going to put the SEM group so that if I treated it with a methyl electrophile, like methyl triflate, for example, it would end up on the correct nitrogen? 3 or 1?
Which nucleophile are you using? Sorry.
So what my question for you, Fang, is where do I put my SEM group so that after treatment with an electrophile, my methyl group ends up on C1. Do I put it here or do I put it here? We can do both and see what happens.
You probably get N3
Yes.
methylated.
Right. So we're going to put the SEM group here. We're going to put a bromine here. If you treat this with methyl triplate, it's going to dock here. And then the triplate will kick off the SEM. Now, where does this thing come from? Well, that's just a simple bromination. And so your starting material is simply something like this. Where you can take this compound, you can do a Suzuki if you want, you can put the SEM1 group on first, then do your Suzuki, and then your brominate, the only available position, and then you switch the methyl group over to the desired one just by treating methyl triplate. So see how this procedure, this understanding of how to dance is so valuable, and think about it putting together imidazoles. It's kind of complicated. In fact, we've got a section on that. For all the sort of topics that are complicated in heterocyclic chemistry, we've got a topic in the book on it. So let me direct your attention to this one. I hope it doesn't scare you, but this is a cheat sheet for you in the book that you could study. You can, of course, make notes yourself, but here's the way to navigate the roadmap of imidazole substitution. It's your cheat sheet of how to do it. Various SEM tricks can be used. It'll teach you about which ones can be deprotonated, which CH1s can be protonated, and when. All of this is in the book, and all well referenced. And so this is a little introduction to something which is a little bit more complicated. And so if you're in a company, this could be a very useful thing for you. And if you're taking it for a grade, it's something you should probably, you don't need to memorize. The great thing about this book is you don't need to memorize anything. You just need to understand it. Once you understand it, you can draw this yourself. So all of this is sort of easy to rationalize based on first principles. As long as you know the first principles, a cheat sheet like this is not complicated at all. It doesn't require memorization. It just requires that you understand. Okay. All right, so we're doing great on time. We have 8 minutes, and this is all we have to cover left, unless there's any other questions. And one of these is problem today number 5, a classic synthesis known as the Dondoni aldehyde synthesis. And so it takes together the concepts we just talked about in a slightly new setting, which is a thiazole. So we need someone here. This is problem today number 5 is probably worth a hearty amount of pyridone. We'll let someone volunteer, or if there's no volunteers, we'll pick on someone.
I'll jump in.
Okay.
All right, what do you say, Alex?
Yeah. So the first step, the nitrogen is like pyridine-like, so it will attack the aldehyde.
Now what do I do?
The negative oxygen can pull off the TMS group. And then that'll give you like a Zwitter ion on the heterocycle. And that anion can then do.
Too fast. 1 second.
Sorry.
Sorry. Now what do I do, Alex?
Attack a second equivalent of the aldehyde at the carbon. And
now what do I do?
then you can play that same TMS trick, and that'll give you back an equivalent of the aldehyde also.
Awesome. This is the Dondoni. Now, Alex, to get even more pyridose, can you tell us what the oxidation state of this position is?
Acid.
Yes. And you'll notice that the product in the Dondoni aldehyde, so this is the canonical one, which is shown down here, is an aldehyde. So conceptually, what do I need to do to this thiazole to get me down to the Dondoni aldehyde?
Reduce it by one oxidation state.
And how am I going to do that with these set of conditions? I've got this methyl triflate and then borohydride, and then this is not an organometallics class. I'm just going to say oxidant. So what's the first step doing? Let's focus on the heterocycle. So I treat this compound with methyl triflate. What happens?
You'll methylate at the nitrogen.
Now what?
And then I guess the CN bond will be reduced.
Now, what oxidation state is that carbon?
The aldehyde.
And then a general oxidant. In the old days, they used mercury. You can use hypervalent iodine. These folks use copper. And then this is just hydrolyzed to the corresponding aldehyde. That is Dondoni. What things did I not mention today? I didn't mention pyridine and oxides. And in the last couple of minutes, that's a really important topic for me to cover very quickly. And luckily, we've done the hard work of covering pyridine and oxide already in the pyridine chapter. So when you think about substitution on pyridine, we're going to talk a lot about some of the most popular ways of substituting pyridine tomorrow and especially on Monday. Another class that we don't talk about so much, when you think about what pyridines do with electrophiles, obviously with acids, they give salts. With Lewis acids, they form coordination complexes. They form ligands, as Nick, of course, is making a bunch of those ligands in his lab. With halides, they form reactive complexes like pyridinium trihydrobromide. With acid chlorides, they give acyl pyridiniums. We'll talk about the reactivity of those types of things. With aminating agents, they give N-amino derivatives. But with oxidizing agents like MCPA, for example, you get pyridine and oxide, which is one of the most useful types of ways of derivatizing a pyridine because of all the variety of things you can do, which usually involves, as we'll talk about tomorrow, ortho types of reactions where the pyridine and oxide is rearranging, you're losing the oxygen, re-aromatizing after nucleophile adds, and that gives you out a sort of a substitution adjacent to the nitrogen. You can do a lot of different types of reactions. I really strongly recommend you spend, I don't know, 1 minute. That's really all you need, 1 minute on this chapter. You can look at this page for a minute. You can tap on these different numbers and it'll show you sort of examples of all these things. But a really useful broad summary of the interesting things you can do with a pyridine and oxide, which is one thing that kind of belongs in this lecture, but there was no time to talk about it today. So with that, we are done with lecture 1 of 3 of the general reactivity phenomenon of heterocycles. How do you substitute them to get the right compound you want? Of course, the lectures after the third one are going to be all about the multifaceted ways of making them, but we have to get through, even though it is quite tedious, we have to get through the ways of rationalizing substitution. And that's what this lecture was all about. So we'll see you for the next installment at 8 a.m. sharp on Wednesday. Have a great day, everybody.